Welcome to this video, which is going to go through one of the applications, one of the first applications anyway, that you'll get into involving differentiation. We're going to look at certain types of motion problems. They're referred to as rectilinear motion questions, which involves particles that are either moving side to side on a horizontal line or an object that's moving up and down on a vertical line. Has to be one of those two scenarios, so it wouldn't be a method we could use if it was on some kind of a diagonal slanted line. And we're going to try and draw a connection using calculus between displacement, velocity, and acceleration. Well, imagine that you're given a function s of t, I'm just going to make up something here, s of t equaled negative 4t squared plus 8t minus 4. And I told you that this function represented the position of a particle moving along a straight line. Well, if we were to take the derivative, s prime, now normally if we have y equals an x squared, we find the derivative, which is the change in this variable with respect to this variable, which this represents, as we know from our earlier studies, delta y over delta x, the change in y over the change in x. So in this function, x and y had been swapped out for new variables, s and t. So s would take the place of the y, so it's change in s, and t has taken the place of the x, so change in time. Now I want you to think about what this means then. So the change in s divided by the change in time, imagine that s represented position. So here it's saying to you, what would the change in displacement divided by the change in time represent? Well, if you have some basic scientific knowledge from even as early as grade 10 science, your change in position or displacement divided by your change in time is something we refer to as velocity. Well, this symbol is the same thing as s prime of t. There's our first connection. If I start with displacement, let's call it s. S prime then will be a function that represents velocity. Well, in the same fashion, if I then said, well, why don't I take the derivative of the velocity? So now it's the change in s prime with respect to t. Well, s prime is velocity, so this is now delta v over delta t. And delta v over delta t, from your science knowledge, hopefully, you have determined that that is what we know as acceleration. And this would be the derivative of s prime, or what we know then as the second derivative. So there is a really important connection that we will use as we're doing these motion problems. So if I start with a displacement, I take the derivative of my displacement function, I will have a velocity function. If I take the derivative of my velocity function, which I would refer to as s double prime, I will have an acceleration function. At this point in the course, we will only go in this direction. We will start with displacement, take the derivative to get to velocity, take the derivative of that to end up at an acceleration function. Eventually, this will become double arrowed. We may start at acceleration next semester and work our way backwards. However, at this point, we only have to be able to go in the differentiation direction. Okay, so what I've got is a long problem that I use kind of to go through all the different types of questions that you may be asked. Now, on the slides that follow, I have each of these sections kind of broken down, and we just do them kind of individually. So this function, if we read it, says the position of a particle is given by the equation f of t equals this function where t is measured in seconds and s position is measured in meters. Okay, so let's look at these. Up here in the corner, I just keep pasting the function just so I don't lose track of what it is. So remember, this is the position function. It says find the velocity at time t. Well, I want you to make the connection that velocity is s prime. So this is telling me find the derivative. Well, the derivative of this would be 3t squared subtract 12t plus 9. Finished. That's all it says. Find the velocity. S prime is velocity as a function of time. There we have it. What is the velocity after 2 seconds and then again after 4 seconds? So this is saying take s prime and fill the number 2 in for time. That would be 3 multiplied by 2 squared minus 12 multiplied by 2 plus 9. 2 squared is 4 multiplied by 3 is 12. Subtract 24 plus 9. 12 and 9 is 21, so this should be -3. Now, we have to, I let students kind of ignore units as they're doing this, but your answers must have units. They told us that the time was in seconds and displacement was in meters, so this would be their velocity in meters per second. It's also important to understand we're talking now not just speed, we're talking velocity, so direction. This is in the negative direction. It didn't give us really enough details to know whether that would mean one of two things. If we were talking about a particle going side to side, negative would imply it's going to the left. If we're talking about a particle moving up or down, that would imply the particle is moving in a downward direction. So for now, I'll just say it's moving in the negative direction at 3 meters per second. All right, first two were easy. Oh, there was another, sorry, there was a part. It also wanted the velocity at 4 seconds. So it wanted me to do s prime at 4 also. Let's see if we can do this one a bit quicker now. So 4 squared is 16 times 3 is 48, minus 12 times 4, which is 48, and then I get a plus 9, which will turn out to be positive 9 meters per second. Now, this leads us to something interesting that must have happened, because at 2 seconds, it was headed in the negative direction. At 4 seconds, it's now traveling in the positive direction. So here's what I do know. I know that sometime between 2 and 4 seconds, this object changed directions from negative direction to positive direction. That's kind of a segue into where we're going next. Okay, so this is, when is this particle at rest? Well, particle would be at rest if it had no velocity, which indirectly is saying, well, when is the derivative equal to 0? Well, we just did the derivative. The derivative of our displacement function is 3t squared, subtract 12t plus 9, and I want to figure out where this is equal to 0. That's a quadratic equation. These all divide by 3. That would make our lives a bit easier. So it's t squared, subtract 4t plus 3 is equal to 0. This will factor t subtract 3 and t subtract 1, giving me two possibilities at the 3-second mark and again at the 1-second mark. So this particle was at rest at the 3-second mark and the 1-second mark. Here's another thing to keep in mind scientifically. If you watch this arrow on the screen, so as this arrow moves in one direction, and then it now goes in the other direction, this, if you again watching the cursor, in order for it to change directions, it must have stopped first, then changed directions. So often these times, if that's where the velocity was 0, it's there to indicate a change in direction of your particle or the object, whatever it may be in that question. But at this point, that's all they ask. When is the particle at rest? There it is. All right, now it says, well, when is the particle moving forward? That means in a positive direction. In a positive direction would mean that the derivative, the velocity, right? So this is saying, when is the velocity positive? S prime greater than 0. Well, we just did S prime up here. So S prime is 3t squared minus 12t plus 9, and I want to figure out where that's greater than 0. Well, this is a skill that, unfortunately, I find sometimes our grade 12 students are a little weak on. Not that it's a difficult thing, but it's just something we don't do a lot of, but it's solving a quadratic inequality. You basically do it the same way you did the equation, except this is now greater than. So now it's t squared, subtract 4t plus 3 is greater than 0. You want to find the zeros, which are your intercepts. So the zeros, which we just did on the last one, are t minus 3. Now, truthfully, you don't have to be doing all this work over again. Now, notice I've just swapped my inequation symbol for the next minute or two to be an equal sign, which tells me that the zeros were at 3 and 1. Then what I recommend you do is draw a sketch. So you just go here and make a number line. So the number 1 would be to the left of the number 3 on a number line. This is a quadratic that had a positive stretch factor, but it is a quadratic. So if I was to look at a rough sketch of what this looks like, I don't know where the vertex is, but I do know it has to look something like this quadratic. These are your times. These over here, if you put a y-axis, these would be your s primes, your y values off of this function. Well, this was your s prime, or in this case, these would be your velocities. Well, this question is saying, when is the velocity positive? Well, the velocity is positive if you're on the quadratic here or up here. Down here, your velocities would be negative numbers because you'd read them off of this scale, so they'd be negative numbers. This graph then has a positive velocity here, and that would be the time from 0. We don't go into negative time, so 0 is less than or equal to t, is less than 1. At 1, it has a velocity of 0, so it's not actually moving in a positive direction, it's actually stopped. So notice I didn't put an equal sign on there. And then this section of the graph here would be any time you pick greater than 3. So if you picked a time over here, its velocity on the graph would be up here. Therefore, at any time greater than 3. There's the answer to this question. Between 0 and 1 second, at any time greater than 3 seconds, this particle is moving in a positive direction. Oops. Okay. Now, if I look at drawing a diagram to represent the motion of the particle, this is a pretty standard procedure, but it's a very important one that you make sure you understand how to do this. What you do is you make a little table of values. You go t for time, and you go s for position. Not velocity, it's not s prime, it's position or displacement. Where is the particle situated? Here, it's not just random times. It is the start time. Always start with 0. And then you're going to go, in this case, with 1 and 3. So it's start. I'll just note these. So always your start, which is 0. These are anywhere s prime, or your position, or your, sorry, not your position, your velocity is equal to 0. And then your last one, we'll kind of do these two questions together. I would put in here also, because this one says during the first 5 seconds, so then I would put my end time, which they'll always tell you in the question. They'll say, like, how far did the particle travel during the first 23 seconds? So then I would go 0, 1, 3, 23. How far did the particle travel during the first 11 seconds? 0, 1, 3, and 11. Start is always, that's always 0. These are anywhere your derivative or your velocity hit 0. And the reason you pick those ones is because that would be the times where the particle is stopped, which would indicate a change in direction. Now, you're going to fill these numbers, and again, the most common mistake is students fill the numbers in the wrong function. I want the position of the particle, so add 0. If you put 0 in here for t, so 0, 0, 0, you're going to get 0. If you fill a 1 in here, so 1 cubed is 1. Take away 6 times 1 squared, so 1 take away 6 is negative 5. And then I add 9, that's going to give me position 4. Now if I add a 3 in here for the t, I'm going to have to write this one out so I don't forget it. So 3 cubed is 27. 3 squared is 9 times 6 is minus 54. And then 9 times 3 is 27. And that actually works out to be position 0. And then if we put a 5 in here, so 5 to the power of 3 is 125. 5 squared is 25 times 6, that's minus 150, plus 9 times 5. So we got negative 25 plus 45. Negative 25 plus 40, so that's position 20. So that would be position 20. Now when they say draw a diagram, this is what they mean. They want you to put a number line. It does not have to be scaled out. These are the positions along the number line where the particle was situated. So if I look at this, I'm going to start at 0. I'll put 4 there, and I'll put 20 over there. Now here's a diagram that maps out what this particle did and how it moved. It started at position 0. It ended up 1 second later, it was at position 4, which means it went to the right first. And that was at the 1 second mark. At the 3 second mark, it's now at position 0, which means it must have turned around and came back this way again. That's the only way it can end up back here. So there, it ended up at position 0. Well, then at the 5 second mark, it's now back over here at 20, so it must have went the other way. So there's the diagram of how this particle moves. Now this particle, once it starts going right, it never changes direction again. Now students say, well, how do I know that? Because there was no other instance where the velocity hit 0, which means there's no chance for it to stop again to change directions. You can't physically be walking one direction and change directions without stopping first. So if there's no more spots where the velocity hits 0, this particle never stops to change direction again. Now, to answer the question down here then, distance. So it's not displacement, distance. Meaning you've got to add up these segments and figure out how far this particle traveled. Well, it went from 0 to 4, which was 4 meters. It was at 4 and went back to 0. That's another 4 meters. It was at position 0 and then ended up at 20. So that would be another 20 meters. So in total, that particle traveled 28 meters. All right. Continuing on, now it gets into acceleration. So acceleration, we said, is the second derivative of your displacement. So it says, what is the acceleration at time t? Well, let's do s double prime. Make sure we remember what s prime was. So here's my function. So we can see it here. So s prime was 3t squared subtract 12t plus 9. That was velocity. The acceleration would be 6t subtract 12. So that's at time t. This says, well, what about at 4? So put 4 in for t. 6 times 4 minus 12 would be 12. Acceleration's measured in a measure of distance over time units squared. I'm not going to get into the graphs. It just wants us to kind of look at their connection in terms of velocity, acceleration, but I think I'll skip that for now. That's something we could easily do on Desmos if we had that set up and wanted to look at it. I'm more concerned right now with kind of the algebraic manipulation of this stuff. When's the particle speeding up? Speeding up, and when's the particle slowing down? Well, in order for a particle to speed up, so a lot of times, this would be a class discussion we would have, and we get all kinds of scientific jargon gets thrown out, but sometimes students kind of forget to look at the big pictures. They'll say, well, it's speeding up if it has positive velocity. And somebody else will say, no, it speeds up if it has positive acceleration. Now, unfortunately, both of those are incorrect. In order for an object to speed up, I'll give you an example. If I was to go to the top of the school and hold a ball in my hand and let it drop, that ball, I hope you would say, is going to speed up. But if you take a ball and drop it down, it's going to have negative acceleration, but it's still speeding up. Well, the reason it's speeding up is because the acceleration is going down and the velocity is also going down. Versus this, I stand here in the classroom, I have a ball in my hand, and I throw it up in the air. That ball is going to slow down. And the reason it's going to be slowing down is because the velocity I gave it was in the positive direction, but the acceleration is pushing down, right? So those two get working against each other. So in order for a particle to speed up, what has to happen is the velocity would have to be positive and the acceleration would be positive, or the velocity would be negative and the acceleration would be negative. So the velocity and the acceleration just have to be working together and not against each other. So let's look at an example of one of those. So let's take speeding up. So speeding up, I'd have to have s prime, which we did earlier. So moving in the positive direction. So velocity greater than 0, we found was between 0 and 1 and greater than 3. So that's where the velocity is positive, and here's where the velocity was negative, down here between 1 and 3. All right, so let's keep that in mind. That'll help us. Oop. So s prime is greater than 0 on a number line like this. So 0 to 1, say 3 is over there. These are the intervals where it was greater than 0, between 0 and 1, including 0 and 1. No, actually it was open at those. And then any time greater than 3. Now if I look at s double prime, which is the acceleration, in order for it to speed up, the acceleration would also have to be positive. With the acceleration we just did on the prior slide, there's your function for that, 6t minus 12. So 6t minus 12 to be greater than 0 would only happen if t was greater than 2 seconds. So I'll go to my number line here. 2 would be here somewhere. Greater than 2 seconds. Looks like that. So visually, if you're a visual person, we're looking for where this and this are both true. So when you're looking at graphs, and these are called sets, what you would be looking for is the overlap. Where were both of these concepts true? Well, both were true here. So at any time, so this is only the first possibility, at any time greater than 3 seconds, both the velocity and acceleration were positive. Well, now you have to look at the other possibility. So the other possibility is the velocity could be negative and the acceleration could also be negative. Well, then they're both going to work together in a downward or left direction. And now let's number line this one. So on a number line, we have our 0, 1, 3, 2. So it said negative direction was between 1 and 3. So 1 and 3. 1 and 3. This is velocity less than 0. Remember, here's in blue was where it was positive. So in between here and here is where velocity was negative. So that would be all of those possible times. Now for s double prime to be less than 0, that would be 6t minus 12 less than 0, 6t less than 2, less than 12, t has to be less than 2. So that would be from here forever this way. So the overlap of where both were true is right in here. That would be another spot then where this particle would be speeding up, because at this interval, both the acceleration and the velocity are negative, which would mean any time between 1 and 2 seconds. So the answer to the question is, when is the particle speeding up? So it speeds up in 2 different intervals. This one, so between 1, there should be no equal signs on those, sorry, because at 1 and 2 it's actually stopped. We mentioned that earlier. I didn't have you guys to fix me here. So this should be just less than, no greater, no equal sign. So 1 is less than, t is less than 2, or the other one over here was any time greater than 3, or any time greater than 3 seconds. This is in seconds. There's where it's speeding up. Now the slowing down would be the opposite. You would want this to be positive, but you'd want this one to be negative. And you'd want this one to be negative and this one to be positive. That would have the velocity and acceleration working against each other. I'm only going to do the speeding up part. You could, it's same idea, draw the number lines, look for the overlap where both are true. All right, so that's how you deal with speeding up and slowing down. There's our graph, and that's it. So that's kind of a look at the different types of questions that you can be asked. So I grabbed a couple of examples off of old tests just for us to use. This one was off a, I believe it was a UMB exam, if I remember right. Let's see what they ask. It says a rock is thrown upward on Mars with an initial velocity of 19 meters per second. Its height, so this is a height function. It says, what is the acceleration of the rock at time t? Acceleration, hopefully your brain thinks second derivative. So I need to find h prime of t first, which would be 19 minus 3.8 t. H double prime of t is negative 3.8. We would be in meters per second squared, which basically tells me that must be gravity on the planet Mars. Relatively easy question. It says, how fast is the rock going when it hits the ground? Well, how fast is it going is going to be found using s prime. That's the velocity. When it hits the ground, well, the issue is I'm not sure when it hits the ground. So what's the time when it hits the ground? Let's figure that out. That would mean, so think about this. Now you got a rock. I think it was thrown up first. Yep. So a rock is thrown upward. Well, it's going to go up so high, but then it's going to stop. And then it's going to fall back down, and it's eventually going to hit the ground. Well, I'd like to know what's the time when it hits the ground, because if I know the time, I can put it in s prime and get the velocity. Well, let's take our function and figure out when it hits the ground. So when it hits the ground, right here, the position, s, should be 0. So take your position function, which is 19t, subtract 1.9 t squared, and figure out when that height will be 0. Let's take out a negative 1.9 t. That will give me 10 minus t equals 0. So this multiplied by this with an answer of 0 could only happen if t is 0, which makes sense. That's the beginning. So the rock must have came from the ground. And the other time then would be the 10-second mark. Well, that's the second time. So it started at 0, went to its highest point, came back down, hit the ground at the 10-second mark. So what I want is s prime at 10. Well, I can't do that until I know what s prime is. Well, s prime is the derivative of this. So s prime is 19 minus 3.8 t. So s prime at 10 would be 19 minus 3.8 times 10. Too many brackets on the go here. Let's fill that in again. So that's 10-second mark. That's going to give me negative 38.19, so negative 19 meters per second. Negative makes perfect sense because at the time it hits the ground, it should be traveling downward. That would be the answer. And again, as I told you, that came off of a university final exam. So I don't want you to think that just because it's university, it's going to be a big challenge. Those two questions were very, very straightforward. All right, one more. This, I believe, came off of one of my old unit tests. So it says a particle moves according to the law of motion. It gives you this. Determine the velocity of the particle when it has an acceleration of 2. So it's giving you the acceleration. Well, let's make some connections here. So s prime, which will be my velocity, 6t squared, subtract 18t plus 12. S double prime, which will be my acceleration, is 12t minus 18. Now it says determine the velocity. So to determine the velocity, I got to substitute a time. One of the big mistakes students make is they just fill 2 in for t. This is not a time, it's an acceleration. Well, remember that S double prime means acceleration. We're going to replace this left side with a 2 because that's what I want the acceleration to be. And I'm going to determine the time that will give me that acceleration. Oops, minus 18. That's a minus. So bring your 18 over, you're going to get 20 is equal to 12t. Divide by 12, divide by 12. Grab my calculator here. So 20 divided by 12, 20 divided by 12 is 1.667, 1.667 seconds. That's not what I was asked, though. I was asked, what is the velocity at this instant? So now I'm going to put that number in here for my time. And that will give me 6 bracket 1.667 squared. Subtract 18, 1.667, and plus 2. A negative 11.333 meter. It doesn't give us meter, it just says units. So let's call it units per second. It does give us seconds. Anyway, we knew it was seconds, but it doesn't give us any measurement unit. That's part A. Part B. When is the particle moving in a positive direction? So in a positive direction would mean right or up. That happens when S prime is a positive number. So we got to figure out when the velocity, which is 6t squared, subtract 18t plus 12, when would that be greater than 0? That's called a quadratic inequality. So we need to find the zeros. Easiest thing to do here is to get the numbers to be a bit smaller first. T squared, subtract 3t plus 2. Instead of greater than 0 for a moment, I'm just going to put equal 0. This would factor to be t subtract 2 and t subtract 1 is equal to 0. So at the 2 second mark and again at the 1 second mark, that's when the velocity is equal to 0. So if we map that out on a number line, there's your 1 second mark, there's your 2 second mark. It's a quadratic, it opens up. So it looks like this. I'm looking for where that quadratic is greater than 0, which visually means above the x-axis. Right, these are your velocities on here. So it would be anything over here, or any number you pick over here, you would hit the graph up in the positive part. Remember, we can't have negative time. So 0 is less than or equal to t is less than 1, or if the time is greater than 2 seconds, you would be moving in a positive direction. Negative would be this loop on the bottom. 1 is less than or t is less than 2. And then finally it says, sketch the path of this particle and figure out how far it has traveled during the first 8 seconds. So to do that, I need to make a table. We talked about this, time and position. So in the beginning, anywhere the velocity hits 0, and then at the end. So this one wants it over an 8-second interval. So that would be my end time. Now remember, these are going into the position function. I'll just jot it down again over here. So position was 2t to the third, subtract 9t squared, plus 12t plus 1. So you're going to fill 0 in here. So 0, 0, 0, plus 1. You're going to get a 1. Fill 1 in here. 2, take away 9, negative 7. Plus 12 is 5, plus 1 is position 6. Substitute 2 in here. So 2 cubed is 8, times 2 is 16. 2 squared is 4, times 9 is 36. 12 times 2 is 24, plus 1, so that's going to give me 24. 41 minus, so position 5. And then at 8, I'm going to grab my calculator for this one. So it's 2 times 8 to the power of 3 minus 9 times 8 to the power of 2 plus 12 times 8 plus 1. And that puts me at position 545. So let's map out how this particle moved around, and let's kind of do it on the left-right kind of scenario. So position 1 is the smallest number, and we've got 5, and we had 6, and then way over here we had 545. So here was what happened. At the beginning, it was here, position 1. It then went to the right. At the 1 second mark, it was at position 6. So it went from 1 to 6, and it went that way. So let's kind of tally our distances at the bottom as we're going. So it's at 1, and it ended up at 6. So a lot of the mistakes students make say, oh, so it traveled 6. No, because it didn't start at 0, it started at 1. It started at position 1, ended at position 6. That's a distance of 5 units. Plus, at the 2 second mark, it's at position 5. So it must have turned around and come back this way. It was at 6, ended up at 5. That's 1 unit. That's the 2 second mark. The 8 second mark, it's now at 545. So it must have stopped here, which is why you had your velocity 0 at that point, and then it went the other way again. Now it was at position 5. It ended up at 545, so that means it traveled a distance of 540 units, giving me a total distance traveled of 546. Didn't give us any measurement unit. We'll just say units. Okay, so that is how you map out the path of an object or a particle, and you determine its distance traveled. Now, students will often just plug in 8 here. They get an answer that's close. They say, oh, I'm close. No, that's displacement. Don't confuse displacement, which is the position of the particle at that instant. It doesn't factor in how the movements it took to get to that position, which is what you do with this diagram. All right, so that is a rundown of how you go through rectilinear motion problems involving particles moving either in the left-right direction or the up-down direction, and some of the concepts that go with them and how it ties into velocity, position, acceleration, and how those three are all intertwined in terms of derivatives. So hopefully this helps you with this concept, and best of luck with the practice questions, and there'll also be a formative assessment to go with this stuff as well. Thank you for watching.